Welcome to Lab 6 in Compute 127. This lab will focus on input and output from files, file I/O for short. And the goal here is to be able to open a file, write to the file some data, and read from the file later. So we're going to work with files as they're stored on the hard drive. And these are files that will stick around. So when you usually until now what we've done is we manipulated data that was in memory, and now we can save that data from memory onto the disk and read back from it in future invocations of your program. So it kind of sticks around on the drive. When you turn your computer off, it will persist. So it's mainly we are dealing with persistent storage. The interfaces are very general, so often the same interface is used for reading and writing from the terminal or from strings or from the network, and so this is a fairly general interface that we're going to explore. But the primary usage in this lab will be to interact with files on the file system. The setup for this lab is really simple, and I think you're all used to setting up your repository for the lab, for each lab now. So it's pretty much add a new directory called 6 for lab 6, and then that'll be the working directory. So let me just show you here that I'm in my repository for Compute 127, and when I go in to the directory for 6, the main files I have here are you will be continuing with the data structure that we introduced last time, which is int array the int array _t data structure, and so we'll be using the same int array.h file. We'll be using the implementation of the functions from the previous lab, lab 5, and then you'll create a t1.c for the first task and a t2.c for the second task. And what I've done here is I've added 2 test files. The first test file for me is to test task 1. You can name this test file anything you want. You have to name this file t1.c. You have to name this file t2.c, which contains the implementation of task 1 and task 2 for lab 6. But your test files can be anything you want. So I have 2 test files, test binary and test json. Test binary does all the tests for task 1, and test json does all the tests for task 2. And I've created a makefile just to help me compile the file. So when I type in make t1, it's going to compile int array.c along with my test binary and t1.c to create a file which is, you can see this -o t1 creates a binary called t1, and when I run t1 it will do all the tests to make sure that my implementation of task 1 is correct insofar as my tests are concerned. And then of course once you're confident about your tests checking your program, you can commit and push your task t1.c, and you'll get the autograder output, and those tests will run on your code. So in this lab, when we are dealing with files, there are 4 basic operations that we're going to be doing. The first one is to open a file, and so this will look for a file in the file system and open it and give us what's called a file handle. That's usually a capital F file pointer, and so this file pointer is often referred to as a file handle because it's what we use to access the file. And the first function is fopen, and fopen simply gives us the ability to open the file. And this is a function that we use both for reading from a file and also to write from a file. So the arguments that it takes is a file name, so that's just a string or a char star, and it also takes a mode, and the mode is the mode in which you want to access the file, either a read or a write. So we'll see an example of that. And then we can either write to a file or read from a file. And the nice thing about this interface is that you can see here that the different arguments to these two functions are exactly the same. So they both take a pointer to something. The pointer to something is where we're going to get the data to write or put the data that we read from the file. And then we get a size, and the size is just telling us what is the data type that's pointed to by this pointer. So this pointer might be pointing to a integer array, in which case we want to say that each item that we get is going to be of size integer. And then we say how many items you want to get. Again, the number of items is both in the write and in the read, and that tells us, hey, I want to write these number of items of this size from this pointer, and I'm going to write it to this file pointer or file handle. And so notice that exactly the same four things appear in the read function, except they have, so in one case you're reading, in the other case you're writing, but the function interface is exactly the same. And finally, the last thing you should do, which people tend to forget to do, so try to remember to do it, is to close the file. When you close the file, all of the stuff that you wrote to it will get what's called flushed out to the stream. So you close the stream, and that makes sure that the file is closed and all of the data that's in memory has been written out to the file. So especially when you're writing, but even when you're reading, it's very important. Once you're done using the file, when you're done writing everything or when you're done reading everything, you should always use fclose on the file handle in order to close it. All right, so to get you familiar with these functions, in order to read and write data from a file, the first thing we're going to look at is reading and writing binary data from the file. So we're just going to write a bunch of bytes to a file, and then we can see how to read a bunch of bytes out from a file. So in order to do this, I'm going to write an example program. I'll just call it fwrite.c because I'm writing to a file. And all of these functions that I'm going to use are defined in standard i.h. And I need a file name to write to. So instead of hard coding the file name into the program, I'm going to use the command line arguments. So I'm going to say that the file name is in argv1 because the program name will be in argv0. So in order to write a bunch of data to the file, let's create a data array. I'm just going to create a simple one. It just has 5 elements to it, and I'm going to create, remember that it has 5 elements in this array called len. And now the first thing I need to do is to create a file handle. So, and in order to do that, I have to open something. So I'm going to open argv1. So I'm going to assume that somebody has given me a file name. So it's probably a good idea to check that this file name exists. So I'll put that as an additional check once I finish this statement. So I'm going to, this is the mode in which I'm going to open the file. So file, this file star f is going to be a pointer to a file that's returned by fopen. And the file name it's going to create for writing is the file name that I give as an argument. So I want to make sure that if argc is less than 2, then I just say I need a file name and then exit with an error. So I'm just going to say return 1, and so now this just makes sure that I have an argv1 as an input. And now I've opened the file. Now what I want to do is take this data and write it to the file just as bytes. So I just want to write a bunch of bytes to it. You do need to check that the opening succeeded. So typically you do that by saying is f equals null. That's the error condition. So it means I could not open the file, right? So it just gives an error message and then exits the program. So it's always good to check for errors like this, just to make sure that the files, especially when you're dealing with the file system, your file system could be full, your file system could be missing, and you think you're writing to a certain file, but it actually doesn't have access to it. So it's always good to check for the error condition. Okay, so now I want to write the contents in this pointer. So this is data. Here is a pointer to this sequence of integers, right? It's an array of integers. An array is just a pointer. So I'm going to use fwrite. So I'm going to use fwrite to write out this data. So data is the pointer I want to write. Its size of int. So like each element is size of int. And the number of items is len, because I've remembered that before. And the output is going to write to this file handle f. So one thing to check is an error condition again. If fwrite is not equal to len, that means something went wrong. So I want to say could not write data and then return 1. So that's another error check. And now I want to make sure that I close this file. And once I do that, everything has succeeded and I can exit this program. So you can see that you first need to open the file, then you write as many bytes as you want to the output, and then you close the file and then you can exit. So that's the program to write a bunch of bytes. In this case, it's writing the bytes, the integers that are in this data array, onto a file. And the way that the a.out is the default binary output, and then I'll give it an out file as the first argument, so that it's going to create a file called out file and write these bytes to it. So if I just cat out file, it looks like nothing happened, right? It's not showing me anything. But that's because out file is a binary file and it doesn't really have output that you can see as text. So text files can be viewed on the command line directly, but if something is not a text file, it's a binary file, then it cannot. So you can do a hex dump, and you can see here that it has written the number 1, followed by the number 2, followed by the number 3, followed by the number 4, followed by the number 5, and then the file just ends, right? There's no EOF, there's nothing, because this is a binary file, and it exactly contains 5 integers of value 1, 2, 3, 4, and 5. There's nothing else in the file. So there's no extra stuff that we expected, like when you have a text file. There's no new lines, there's no end of file, there's nothing. It's just a binary file. So one thing you notice when you look at this output file that we created, the out file, is that all of these integers, 1, 2, 3, 4, and 5, are all sort of contiguously one after the other. So you can ignore this. This is just showing you an index of where you are in the file. So just ignore the first column. It's not actually in the file. It's just a way of easily paging through the file. So you can go to a certain byte in the file if you want to. So that's just something that hexdump gives you as an extra notation. What's in the file is actually just this sequence followed by this sequence, right? So it's exactly 5 integers one after the other, and they're contiguous. So it's almost like you have a sequence of bytes in memory, a sequence of integers in this case in memory, have become a sequence of contiguous, contiguously laid out integers in a file. So the file just contains a sequence of integers. So the advantage of this is that we can in fact read a sequence of integers directly from the file, just like we would read an array or write an array in memory. So that's one of the nice properties of reading and writing binary data, is that you can read into memory contiguously from the file. So let's do that. So let's take this out file and just read from it and put it into memory. So what I'm going to do is I'm going to actually start from the fwrite.c file that I had and call it fread.c, and I'm just going to modify it to be able to read from the file. And you can see that we don't really need to modify it a lot. So I'm going to edit fread.c, and in this case I don't know what the data is, so I'm just gonna make enough room for the data. I know that so I'm making an assumption here for this example that I know the length. Okay, so we'll talk about the case where we don't know the length a little bit later. For now, just assume that I know that I'm reading 5 integers from a file, which is not totally realistic, but for this example I just want to show you how fread and fwrite work. So the fopen looks almost the same, except we're not writing a file, we want to read from a file. So the mode we're going to change to R. We are still going to use a file name argument just like we did for fwrite, except this time we're reading from the file. And then we also check for the error in the same way. If f is null, then we say we could not open the file. So far everything is the same. Now let's look at fwrite and just change it to fread. So the interface is so well designed that that's literally all I have to do. We're just going to read into this memory location something which is of size of integer, and we're going to read all of it. So we're going to just read all 5 integers using a single function call. So fread takes care of that, and if it gives an error we can say we could not read the data. And that's it. That's actually all we have to do. So when we save this file, we're going to compile it, and now it's created an a.out file. I have to give it a file name argument, and it's going to read it, but nothing happens, right? So we did not actually test whether we read everything. So what I want to do is, in order to just test that we've read something, I'm going to create a for loop, and the for loop will be going through the array and just printing it. So we'll just print out the contents of the file that we just read. So data I. So what this does is just helps me check that the file, that I read the file and I produced the array correctly. I'm just going to print out the array. So what I'm going to do is compile it and then run it on out file, and you can see it prints out the contents of that file, which was a binary file, but now it's just printing it out on standard output using printf, so I can read it. So I can read that the file contained integers 1, 2, 3, 4, and 5. So one thing we did not consider is what happens if I'm reading and writing from a file, but I don't know the length of the array I'm going to read from it. Or maybe the binary file actually has some structure to it. Maybe it has 2 arrays, and maybe there are different lengths. So there's all kinds of different types of binary files. And how do I deal with that? So let's just look at an example. This is an example that's on the Lab 6 webpage. And this is an example that considers saving a image file, the image file that you're familiar with from your previous labs. And so basically we have columns, which is a integer, which is 32 bits long, and a column and row, which is a 32-bit integer as well. So it has a certain size defined by this type. And so we have columns and rows, and pixels. It depends on, so each image is not the same size. There's some images that might have a bigger width and height, some which have a smaller, and we want to be able to load, save and load variable length, variable size images. So we don't want to say that all the images have to be a certain size, and clearly we want, this is a binary file that we're going to write. So this function called image save takes an image. An image here contains, it contains 3 things. It contains the columns, the rows, and the pixels. And we want to write it out to a file name. So the first thing we do is we open the file name in writing mode, because we want to create the binary file that corresponds to the image. And the first thing we do is we create what we call a header. The header is simply 2 integers. The image, the columns, and the rows that are in this image data structure. And we create an array of size 2, and we create this array of size 2 in order, and we call it header here. And what we're doing is we're going to use fwrite to write down 2 integers of this type, uint32 type. And we're going to write it to the file name, and this is going to be our image header. It contains the number of rows and number of columns, the columns and rows of the pixels that are going to be coming as a subsequent step. So what we do is we compute now the product of the columns and rows, and now we write all the pixels as if it's an array of pixels, right? So the image data structure contains this array data, and each element of data is 1 pixel, right, of this size. And len, as we just computed, is the product of the number of columns times the number of rows, and we write that out. And when we do that, we close the file and we return 0, saying that we've successfully written the image. So notice that the structure of this, when we have variable size objects that we want to write out as a binary file, is the first we write a header, and that header will tell us the size of what to expect in the second stage, which is we're writing out basically the whole size, the whole image, all of the pixels using this array. In order to, so why do we write this header? Well, what we can do when we read it, so let's look at the image load function. The image load function takes an image. So this is where we're going to store the image, and this is the file name. The file name is where we're going to read the image data from. So we're taking a binary file which contains an image. The first thing we do is we open the file, and we open it in read mode because we're reading it and storing it into this image, this pointer that points to an image. The first thing we do is we read the header, as you'd expect. So we do an fread, and we read the 2 integers. These 2 integers header 0 and header 1 contains the columns and the rows for our image. Now we know how much data to read from the rest of the file. So we know exactly how much we need to read. Well, it's the number of columns times the number of rows. And before I read it, I do a malloc so that I can have enough space to store what I'm reading from the file. And then I give fread the pointer to this allocated memory, and I say, okay, load up this pointer with these many pixels. So I know how many pixels because it's just columns times rows. And so with the single fread file, I read all of the pixel data into the pixel array. And then since I've actually set, I'm getting as input a pre-allocated image structure. So I don't need to return it. Your interface might look different. So for example, some interfaces might have a load which returns a pointer. So in those cases, you might have to allocate the location of where you want to save the pixels. But in this case, we have already assigned the data into the image. We also have assigned the columns and the rows. So we're all set. We can return 0 in this case because the image data structure has already been modified with all the information from the file that I just read. So in order to use it, I would load an image. I could even do something to the image and then I can save the image. So anytime I save it and I can load it. So all of these, the image data that I have can be loaded and saved. And a PNG file is exactly like this. It's a binary format for an image. It just has a very specific header. It looks a bit more complicated than the simple header that we've created here. So this is, I think all of these examples hopefully will give you enough of the concept of how to deal with reading and writing files, binary files. And the same idea applies to reading and writing non-binary files. So the second task that you have to do is to serialize an array of integers into a JSON output. And this, the idea here is to take your binary data in memory and save it as an ASCII file that contains a structure. So JSON is a commonly used data format for the web. It's kind of the native sort of serialization or file format for JavaScript, and it's the de facto kind of representation format that's used on the web. And so what we're going to do in task 2 is to take your int array and write it out as a JSON array. Well, one thing to be careful about is we're not actually producing all the full range of JSON outputs. It's a very specific JSON output that just has integers in them. So you don't need to have a general purpose JSON reader or writer. It's very specific to int arrays. So just follow the requirements carefully so that you don't do too much. All you need to do is to be able to write out a JSON output file and then read a JSON input file that has been saved using this kind of function. So if it's your implementation and assuming it's right, then this load JSON should be able to load the JSON output that was created using save JSON. All right, so this lab should be pretty straightforward. You find yourself accelerating your speed of development hopefully by now. So it will be an interesting exercise, and by the end of this you should be able to manipulate files, read and write files, etc.